Hello guys. Today I'm just going to talk about I'm going to talk a little bit about the Newton's approximation method, okay, for finding zeros of a function of an equation. So let's just say that you got an equation like y equals x plus 3, okay? You want to find the zero of this equation is where the zeros of the equation are the points in the graph where this equation represented by a graph is going to cross the y-axis, okay? So you got the x-axis here, well, it's going to cross the x-axis, not the y-axis. So you got something like that, okay? So where it crosses the x-axis here, that's the zero. If you got a function kind of like that, you know, it crosses here, it crosses here, it crosses here, these are the zeros. The things that as the equation gets a larger and larger power, for example, x squared plus 3, try to imagine that you have an equation like this. You got a1, okay, which is the first coefficient, x to the 103, plus a2, x to the 102, plus a3, x to the 101, okay? So you're going to have like 103 coefficients plus the independent term, 104, coefficients and terms, okay, 104 terms in here. So that's going to be very complicated to find the zeros. So one way that Newton invented was to find its approximation method, all right? And the approximation method is kind of related, well, it depends, the function has a bunch of restrictions. It should be more linear than non-linear, okay? And for example, when you get to, I'm going to explain to you guys what happens. First, I'm going to talk about the algebra, okay? So when we're talking about linear equations, you have the slope-intercept equation and the point-slope equation. So we're going to talk about the point-slope equation. Remember, from high school, you have y minus y0 equals the slope times x minus x0. Okay, this is kind of like what we're going to do. The slope, we found out that it's the angular coefficient of the tangent, and this is the same as the derivative of the function at the point, okay? So you see, we're going to replace this function here for something like this, y minus f of x1. Now what is f of x1? Because in high school we say y0 because we're just talking about a linear equation like this, and you got a point in here, and this point has coordinates y0, x0, y0, right? Well, in this case, we're gonna replace y0 with f of x1. x1 is an estimate that you're going to create to be close to one of the zeros, okay? So you're not going to find the zero immediately, but by inspection, maybe there are going to be some methods that you can use to find something that's close. So x1 is not going to be the zero, but it's going to be an estimate of the zero, something that's close. Okay, and then you have the rest of the formula here, which equals the derivative of the function at x1, which is the slope of the function at x1, okay, times x minus x1. All right. Now, in order to find the zero, because you want this x in here, this x over here, to be closer to the zero than this x1, okay? For example, what I'm trying to say is this. Let's just say that you got this, okay? And then you have something like that. So x1 is going to be kind of over here. And the next step, which is this x in here, you want it to be a little bit closer to this zero. Okay, so let's just say that the function's coming here and it's doing this. So visually, what's going to happen is this. You're going to start here. And then you have a slope, right, that crosses the thing kind of in here. All right. Now you want yeah, because I really did this well. So well that it was too well. Maybe, hold on. Maybe something like this. I don't know. Let me think. Let's see if this works. So what's going to happen is that you have this here, and from this point you're going to find the tangent. Now the tangent goes both ways, right? It goes up there, but it can also come down. So it comes down and it's going to cross the y-axis here. I mean, it's so nice that it's crossing very close to the zero, and I don't want that. Let me try to put it a little bit more like that, kind of like that. Okay. All right. So you have a tangent here at this point, and it crosses the x-axis. The x-axis right here. Okay. Let's just say that it crosses at the origin. Now, what you want is the distance from the origin, from this new x. This is going to be, if this is x1, this new x here at the origin is going to be called x2, and you want the distance from x2 to the real zero be smaller than the distance from x1 to the real zero. So if you have the x line in here, okay, in this, I'm going to say that this is the real zero. This is x0, okay? And you start with an estimate here. You want x2 to be closer. So you don't want it to come over here. No, you want it to be closer to x0, kind of like that, x2. And then you're going to find x3, which is going to be on the other side. And you want it to be closer to, kind of like this, to x0, okay? And you want to keep converging. You want to keep converging and converging and converging. Is it ever going to get to x0? No. But if it converges to x0, as you keep making more and more steps, you'll find x1, x2, x3, x1 billion. It's going to get closer and closer and closer to x0. It's just an approximation method. But in real life, sometimes you have very complicated equations, and this an approximation up to 2 decimal points might be good enough, might be precise enough for a saw that you're making, or for a tire, for a car, okay? When you make real life things in the factory, of course you're not going to have God precision, you're not going to have perfect precision, but it's precise enough to the millimeter, to the 10th of a millimeter, to the 100th of a millimeter. It'll be so precise that any more precision than that is unnecessary. So that is what this method is good for. It's just an approximation. Okay? Now, here's what you're going to do in algebra. You already understand the concept, okay? Oh yeah, I didn't finish over here. So, well, it's just that I have a graph that I'm going to show you guys later that's better. Okay, so when it comes to algebra, what you want to do next, you want to make this y equals 0, okay? So what you have is a y equals 0 here, and then you have, you want to isolate this x. So what is this x going to be equal to? If this thing is 0, I'm not even going to write it. I'm just going to forget this y here. Okay, so you're going to have on this side, I'm going to make it slow, f of x1, minus f of x1, f complement of x1, x minus f complement of x1, right? F complement of x1, x minus f complement of x1, x1. Okay. And now you're going to isolate this x in here. So I'm going to bring this stuff over here to the other side. Hold on. I'm going to ignore that minus. Forget about this minus here. And then I'm going to pass this thing here, dividing on this side, okay? So Actually, I did make a mistake. Did make a mistake with the sign. 0 minus f of x1 equals f prime x1 x minus f prime x1 x1. So I'm going to do this a little bit slower. Can't get any slower than that. Okay, this is a minus here, so when it goes to the other side, it goes positive. It goes positive here. Okay, this minus doesn't exist anymore. Now this thing will come dividing here. All right, so x is going to be equal to what? Well, it's going to be equal to x1, okay, minus f of x1 and the first derivative of f at x1. So this is the formula, and then you go like, oh, what is this x? This x right here is actually going to be x2, okay? So you're not going to have an x1. I'm going to transform this into an xk. So an xk here, xk, and this one is the xk plus 1. Okay, so it's the next step, converging on the real zero. All right. Now there's something else that I want to show you guys. This doesn't work always, okay? This doesn't always converge. Now, you see what they want in order to make this, there's a formula that says this. In order for this stuff to converge, you want f of x, xk or x1, xn, whatever, okay? You want f of xn divided, actually times the second derivative of f of xn divided by f, the first derivative of f of xn squared. You want the absolute value of this to be less than 1. Okay, now why less than 1? This less than 1 thing, we're going to talk about this way later when we're talking about limits of convergence. Because if you have something like this, you got an endpoint here and an endpoint here, and you know that within this part you have convergence, you have converging to a limit, okay? Over here you don't have a limit, you have divergence, and at the endpoints you have to actually test at the endpoints, okay? So maybe this one converges, we're going to make it closed, but this one diverges, so we're going to make it open. Okay, so the limit of convergence is this one. It's closed on the left side and it's open on the right side. So if this is A and this is B, the limit of convergence will be x, which is greater or equal to A, and it's less than B. Okay? This will be the limit of convergence. That's where this minus 1 comes from, but I'm not going to explain a whole lot of this right now. What I'm going to show you guys is where the formula comes from, not why you want to make it less than minus 1, but where the formula comes from. Okay, the formula is that they want to derive this whole thing with respect to x. So deriving this part in here with respect to x, this is what you get. Okay, so differentiating with respect to x, you have 1 minus, and here you use the differentiation division rule. So I'm going to open in here, I'm going to say f prime, I'm just going to say f prime, okay, because of course it's of xk, so I'm just going to say f prime, okay, times the derivative of that. So it's going to be f prime too, so it's f prime squared minus, you have f times the derivative of the second, which is double prime, and the whole thing divided by the bottom squared. So it's going to be f prime squared. Okay, this is just the division rule. Okay, now you have something in here that you get a formula here, right? I mean, you don't have a fraction here, but you do have a fraction here. I want to transform this whole thing into a fraction. So I have to erase this one from here. I'm just taking the minimum common denominator, and I'm going to put f prime squared here. And now everything has the same denominator, so you can take care of this stuff. Look at that. F prime squared minus f prime squared is just going to be 0. Okay? This minus, because you see, guys, you see this parenthesis here? Look, the big one. You want to make this disappear. To make this disappear like this, okay, this thing here has to be negative, and this thing here has to be positive, right? So I'm going to do that. I'm going to make this thing disappear. It's complicated, but hold on. So it's just gone, okay? And I'm going to make this one be gone too, okay? Now, this was positive with a negative is negative. Now this is negative with a negative becomes positive. Okay, so you cut this one with this one and look at what you have. F double prime divided by f prime squared. F double prime divided by f prime squared. Okay, it's the same formula. Okay, so this is a condition of convergence. For x of n. Why do I say a condition of convergence for x of n? Because depending on the function, if you choose a certain xn, because, for example, you have x1, which is an estimate. Remember, it's an estimate of what the x0, the real root, is. Let's just say that it's 1.5. This may diverge. Maybe when you plug this in here, okay, it's not going to work. When you put 1.5 here, 1.5 here, 1.5 here, things are just not going to work. But if you put a 0.7, for example, you put 0.7 here and there, then it works. Then this whole thing becomes less than 1 and it converges. That's why you have that interval of convergence. Okay. Now, of course, I already showed you the theory. I'm not going to show you all the calculations. I'm going to show you proprietary material now from the book, because these things are very nice to be done by a computer in a table, because there's too many calculations. You don't want to do that by hand. Okay, so let me show you guys the stuff. I already gave you the theory. Oh yeah, I want to show you guys something here too. Some graphic. Okay, that's going to be a visual representation of what's going on. So you see here, you start with this estimate because C over here is the real 0. But you start with this estimate here, okay? And then you come and you keep coming, because the tangent could go up, but no, you want to go towards y. So, you want to go towards y equals 0, which is the x-axis. So you get to x2. You see that the distance between x1 and c is less than x2 and c. And then x2, you come here on the graph again, and you get the new tangent at this point, and you keep coming all towards y equal to 0, which is the x-axis, following this tangent at this point, and then you're going to find x3. You see that x3 is smaller than x3 is smaller than the distance between x3 and c is smaller than the distance between x2 and c and x1 and c. Okay, now if you keep going and going and going and going, look at that. You're just going to keep going and going and going. By the time you get here, this thing is going to be like this. This thing here is going to keep coming and coming and coming and coming like that. So what do you have? You have, from here, you have a tangent. You see, it keeps going and going. It's going to meet this thing way in there when the tangent is almost parallel. So look at that. The tangent keeps coming and coming and coming. And then you actually meet that thing over there. Okay? Oh, no. Sorry. I'm getting ahead of myself. Hold on. What I meant was, it starts here at x equals 1. and you get the tangent line and you find x2 here, because when a tangent line crosses the x-axis. And then you come over here, find a new tangent line, and you come over here when it's crossing the x-axis again, which is x3. So you're going to come over here, and from here, look, you're going to get a tangent that's kind of, man, today is not my day. Okay, you're going to get a tangent that's kind of like that, I guess. See, let's make it pretty big. So you have this tangent here. I'm going to make it thick. So you see that this tangent is already crossing the C here? I mean, the tangent from here, from this point, went down and it's already crossing the C, or it's very close to C, so it's converging. So this is a visual example of what's going on. Okay, now I'm gonna show you guys some proprietary material here. This is not mine, all right? This belongs to a book. I don't know what book it is, but it belongs to a very nice math book. So look, calculate 3 iterations of Newton's method, blah, 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 blah. So what is the function? X squared minus 2. Hey, x squared minus 2 is very easy, right? Right here. I mean, the 0 is just going to be plus or minus square root of 2. Let's see here. Very hard for me, even for me to see this stuff. So y, x squared minus 2. So x squared, this thing is going to become a 0. X squared equals 2. X equals plus or minus the square root of 2. So these are the zeros. Why are you doing this thing? Because remember, sometimes you're going to find equations that are not that easy. They're going to be like x to the 505 plus minus 5x to the 502 divided by, plus 1 divided by the square root of 7 times x to the, maybe 1.3 divided by, who knows? So this is going to be very complicated. So this approximation numeric method allows you to try to solve for these zeros much easier. So, okay. So here we go here. You start with the estimate of 1, okay, and then you find f of xn, which is what? F of x1. Why 1? It's just an estimate. So 1 squared, 1 minus 2 minus 1. That's why you have a minus 1 in here, okay? And now you gotta find the derivative of xn when xn equals 1. What is the derivative here? That's 2x. 2 times 1, 2. That's why you have this 2 here. Now when you do this divided by this, you have this thing, right? Because it's minus 1 divided by 2, which is minus half. Okay. Now you're going to do xn, which is 1 minus half. So it's 1 plus half, 1.5. Now you get this 1.5 and you bring it over here to the next iteration. So this is the first iteration, this is the second, then you have the third here, then you have the fourth, okay? And you can see that it's actually converging. The book says right here, yeah, because I already showed you guys that the convergence is 1.414214, right? So you have 1.416, and now we have 1414216. So only this in here is wrong. Everything else is right, okay? So this is a good approximation method. Now, let me show you guys the next one. Here. So now you have 2x cubed plus x squared minus 1 plus 1. Okay, so here you got the formula for the iteration, which is going to be this function divided by this function. And it gives you an estimate, right? The estimate is minus 1.2. It wants you to find out the thing, how can I say, the convergence. Look, continue the iterations until 2 successful approximations differ by less than 0.001. And look at that, that's what happened here. You have 0, okay, so you get here 0.00, another 0, and 1, and you have that. Okay, you can see that this part equals exactly this part. So from the third iteration to the fourth iteration, you have a difference of less than this. Okay, and it's the same method. That's why I'm not gonna show you guys, walk you through these things again. All right? Okay. Of course, the method fails when the method fails when for a certain xn the first derivative, okay, this is just a 1. The first derivative of xn is equal to 0. Why? Because xk plus 1 equals xk, or x sub k plus 1 equals x sub k, right? Minus f of x sub k divided by the first derivative of x sub k. So if this is 0, this thing right here, or if it approaches 0, this thing right here is going to go through the roof, okay? And then what are you going to have? Look, let's just say that this xk, x sub k minus x, minus c, I'm just going to say minus c, where c is the root, it has a certain value, okay? So put this in absolute values. This is less than or equal to, I don't know, maybe omega. All right. Now, if this is going to be huge, this huge thing here is just going to obscure this stuff. And now when you have the absolute value of this huge thing, okay, you can see that this xk here, x sub k plus 1 is going to be this huge thing. So what's going to be, what's the implication of that? X sub k plus 1 minus c is just going to be huge. It's not going to be, it's going to be way greater than, it's going to be way greater and equal, well, it's just going to be way greater, not even equal to omega. So you see that it's not converging, it's not getting closer and closer and closer, it's just going to blow up. So you don't want, the method fails when you get to an x sub k, which is a point, and the derivative of that point is close to 0. And I'm going to show you guys now this thing. Why? I mean the visual, okay? If you have something like this, I'm just going to, okay, that's fine. And then now you have a function like that. Okay, now you see this is c, right? That's where it crosses the x-axis. If you start kind of right here, which is close, you're probably going to converge. See, I mean, it's already converging, you can barely see it. Now let's just say that you start with an estimate here. Now look at that. Okay, look at that. That thing is going to cross the x-axis way over there to the left. Way over to the left. Okay, and then you go to the left, you're going to come here and you're going to cross the function here, and the function here also has a tangent that's very close to 0. It's not going to be 0, but it's going to be very close to 0. And then you're going to cross this point, and from this point you're going to get the tangent and go way over there. Look, you're going way. So you see that you're spacing out. Instead of converging around here, you're actually spacing out. You're going further and further and further and further. So for the same equation, sometimes an x sub k is going to work and another x sub k is not going to work. All right. I'm going to try to undo all this mess in here. I'm going to show you an example here that it fails to converge. Numeric example. Okay, so the function f of x equals x to the 1/3 is not differentiable at x equals 0. Show that Newton's method fails to converge using x sub 1 equals 0.1. So it comes here, x sub n plus 1 equals x sub n minus, f of xn divided by the first derivative of x at x sub n of f at x sub n. And then you do all these things, and the whole thing is just going to be minus 2x sub n. Okay, so if you start with a 0.1, you're going to keep going and going and going, and the result in here, right, because the final formula was minus 2x sub n. So 0.1 here times minus 2 is going to be minus 0.2. And then you have minus 0.2 here times minus 2, it's 0.4. Times minus 2 is minus 0.8, and then you have minus 0.8. You can see that it's spacing out, okay? This, how can I explain this to you guys? You can see, all right, look at this and look at this. Maybe it's just going to be easier to explain why the whole formula has to converge to less than 1, okay? Because look at that. We have x sub n plus 1, okay, equals minus 2 divided by x sub n. So let's see here, they have divided by x sub n. And you put this in the absolute value, okay? If you're putting this in the absolute value, what are you going to have according to this formula here? You're going to have a 2. This is greater than 1. And what did I say? I said, remember that in order for something to converge, because you can see, guys, in order for something to converge, remember that formula? I'm going to show this to you guys again. You have f times f double prime divided by f prime squared. Okay, and this thing has to be not less than or greater, less than or equal. It's going to have to be less than 1. Why? Because of this situation here, okay? Basically, x sub n plus 1 is represented by this, and x sub n is represented by this. So when you have a series, which is what we're going to see later on, okay, you have a sub 1, a sub 2, a sub 3, a sub 4, and you're trying to sum all these, you're summing these things. One of the methods that we can use to see if the summing is going to converge to a limit, if a sub n plus 1 divided by a sub n, if this put in the modulus, okay, or taking the absolute value of this, the thing is going to be less than 1. If it's less than or equal to 1, or if it's greater than 1, it diverges. Okay, so this is you can see this here visually. You got 0.1, multiply this to minus 2, because you got a minus 2 here. So you have minus 0.2, and then you're going to have 0.4, minus 0.8, 1.6, minus 3.2, so it's just spacing out, and you don't want that. Let's just say that it's 1, okay? Instead of being less than 1, it's 1. Is it going to converge? No. It's going to be 0.1 times 1, 0.1 times 1, 0.1. It's never going to get like 0.95, 0.83, 0.71. It's never going to get closer and closer and closer. It'll just stay the same, or it'll blow up, it'll diverge. That's why you have this condition here. That's why you have this condition here. Okay? Okay. So here's a visual representation of the previous example. Why it doesn't work. See? You start with this one here. here, okay? And then you follow its tangent. The tangent comes to 2. Now you can see that the only, how can I explain this? The only root that this function has is at 0, at x equals 0, right? It's right here, this dot in here. That's great. Now, look at the distance between x1 and this. It's this small. Now look at the distance between x2 and this. It's getting larger. Now the distance between x3 and the 0, it's getting larger. And now x4, okay? And now x5, which is here, look. The thing is just blowing up. Why? Because it's following these tangents that are very close to 0. Remember, when you have a tangent that's very close to 0, because the tangent is the first derivative, and the first derivative in the formula appears in the denominator, a denominator close to 0 is going to blow up the formula, and things are going to be huge, and the whole thing would diverge. That's what's happening here. And yeah, I already showed you the condition for convergence, which is f of x times the f double prime of x divided by f prime of x squared, which has to be taking the absolute value of this whole maths, it has to be less than 1, right? Just to finish up, this is the formula that I'm talking about. Okay? You want the absolute value of f, and it does matter, okay? The x does matter, so I'm going to put x sub n, I'm going to put x sub n. And then you have the second derivative of x sub n divided by the first derivative of x sub n. And this whole thing squared, okay? Take the absolute value of that has to be less than 1. This is the condition for convergence. So if you plug in a value here for x sub n and it diverges, it's not going to work. Now if you put 1 that converges, then it's within the limit of convergence, and everything works. And that's Newton's method. And that'll be it for this video. See you guys in the next video. Bye.